Hi everyone. So as Joel's already said, there's going to be some interactive questions throughout, and so the link is here, but it's probably easy to just go in the chat. So if you want to participate, I'd advise getting that up now, just so you're ready throughout when we have them. So I'm Katie Severn, and my pronouns are she and her, and I'm going to be talking about how we use maths in the fight against COVID-19. So first of all, who am I? So I did my A-levels in maths, further maths, physics and chemistry, and I knew quite early on I wanted to do a degree in maths. I enjoyed maths and further maths the most, and in physics and chemistry the parts that really I enjoyed the most were the parts that had maths. And when I came to Nottingham I fell in love with the campus, so hopefully some of you may get a chance to come and visit the campus at some point, because I think that's a real selling point. When I did my degree, I was lucky enough from my second year to my third year that summer to do a summer internship, and I worked with some researchers and got a real idea of what research is like in the School of Maths. And it's from doing this that I really realised that when my degree was over, I wasn't ready to leave academia, and so I stayed to do a PhD in maths, and this was using statistics to analyse texts. So for example, we can use statistics to look at novels and find different writing styles between novelists, and to classify who wrote something, and that's all based using statistics and looking at large data sets. And so this picture is me graduating, and this is the day I handed in my thesis, so that was a good day. I'm now an assistant professor in statistics. So one of the aspects of my job is lecturing, and I lecture a module called Statistical Machine Learning. So many of you might have heard about machine learning. It's being used more and more in sort of day-to-day lives. So something as simple as classifying if an email goes to your junk folder could use statistical machine learning, deciding if a loan's going to be accepted, and it can also be used in medical applications. So for example, looking at a scan and seeing if we can detect any abnormalities in that could be indicative of some kind of disease. So that's why I lecture. Another aspect of my job is doing research, and the current research project I work on is risk prediction for women's health and rights in Tanzania, a novel statistical methodology to target effective interventions. So that's quite a long title, but essentially I'm looking at developing novel statistical methods to help improve the rights and health of women in Tanzania. And specifically for me, I've looked at a large maternity data set and try and predict if a woman may be at risk, and if so, what kind of intervention can we put in place to hopefully increase the chances of positive outcome. Another role of my job that I'm particularly passionate about is that I'm on the Equality, Diversity and Inclusion board within the university. So I'm really passionate about improving diversity and inclusion within the university, and I've done quite a lot of work in the past, particularly focused on STEM subjects like maths. So that's me. So now we'll go over to what I'm actually going to be talking about today, and I thought I'd start with this quote, that there's a mathematical angle to almost anything whatsoever. So day to day, maths is underpinning so much of what we do in our lives, whether we know it or not. And so hopefully it's not surprising to any of you that when we're thinking about COVID, that maths is being used a lot, sometimes behind the scenes, sometimes in more obvious ways. So in the past year, I'm sure we've all been overwhelmed with COVID-19 news stories, and a lot of them are using numbers and statistics within them, and you have to have a bit of a critical eye to really understand what's happening. So these are just some of the headlines and tweets I've seen. So the statistics, what can we trust? What should we ignore? What do they mean in terms of personal risk? What do the numbers really mean? So we've seen quite a lot of confusion when statistics have been being used recently as to what they're actually trying to tell you. And I personally have seen a lot of abuses of statistics where people have used them incorrectly to tell a narrative that suits them. So it's really important when we're thinking about doing maths and statistics to think about the context that we're doing it in, and to make sure we can convey to the public. So a good example is this COVID alert level, and this was I mean, we've had quite a few alert levels since. So this was back maybe 6 months ago when we had an alert level from 1 to 5, and it was published as the R number plus the number of infections. While both of these are positive numbers, the number of infections can range from 100 to 1,000. So how can a sum of a number between 100 and 1,000 equal a number from 1 to 5? The answer is it can't. It's completely incorrect, this equation. It's really meaning that the alert level was taking into account the number of infections, but it wasn't a simple sum. So by somebody trying to convey this in perhaps a simple term for people to understand, they've actually conveyed completely incorrect information. So it just shows that in maths, we need to be really careful of what we're saying and making sure people understand. So before I go on to some of the specific examples of how we're using maths to model COVID, it's useful to have some definitions. So I'm sure you'll all have heard epidemic and pandemic be used recently, but what's the difference? So an epidemic is a disease that affects a large number of people within a community, population or region, whereas a pandemic is an epidemic that's spread over multiple countries. So I've heard people sometimes say, you can remember it because pandemic has a P, which is a passport, because it can travel between countries. Whether that's useful is up to you, but that's how they differ. We also have an endemic, and that's a disease with a constant presence in a specific location. So some examples, Covid-19, when it was just in China, was an epidemic. However, when it spread from China, it became a pandemic. Something like malaria is an endemic because it's constantly present in parts of Africa. And I have heard people say perhaps Covid-19 will become an endemic where it's constantly present. However, hopefully we'll be managing it better. So I've already mentioned the R number, but what actually is the R number that everyone's talking about? So I'm now going to put this quiz open, so if you head over to this app, you should be able to, in a second, get a chance to vote. So hopefully you'll be able to see this, that there's 4 options, so you've got a minute to have a guess. So we've got the options for the R number being how many people will die, how many people that one infected person will pass the virus on to on average, how long the incubation period will be, or an abstract number based on all the above figures. So we've got another 30 seconds left for you to have a vote on what you think that R number is. And now 15 seconds. So I can look at the results. So we've had over 80% of people saying they think it's how many people that one infected person will pass the virus on to on average. And that's the correct answer. So well done. The majority of you got that. So let's look a bit more about the R number because it crops up a lot and it turns out it's a very useful number when we're looking at epidemic modelling. So R can be thought of a rating of a disease's ability to spread. And the true definition is the number of people that one infected person will pass the virus on to on average. So if we look at this little picture here, we've picked an R number of 2. And so this red person is infected, and on average, they will infect 2 other people, which we can see here. These 2 other people on average will go on to infect another 2, who will then go on to infect another 2, and so on. So we can see that just one infected person, after about 4 lots of infections, we've got 16 people infected. So it's increased the size quite a lot. It's really important though to note that it says on average. So I can't know exactly how many people one person will infect, but I'm dealing with averages, and that's what we do in statistics and probability. I don't know exactly what's going to happen, but when I think of a population as a whole, I can think of the sort of average amount that's going to happen. So some people may infect a lot more than 2, Some may infect a lot less than 2, but the average will be 2. Now, you might also see a number called R0, and this is the reproduction number, and it's the exact same definition as R, but when no interventions are in place. So R can vary as interventions come into place. The aim, as we will see, is to reduce the R number. However, R0 is a constant number. We can't change it with different interventions. And this R0 number is useful because it allows us to compare different illnesses and how infective they are, and when there's no interventions. So here's a list of diseases that I've got R0 number for, and if you have a think what you think the most infective is. So again, if you head over to the app, you will get a chance to vote. So it's only a selection, so it's out of Ebola, Covid-19, measles and the common cold. So which one do you think is the most effective of those 4? And some of you may be able to have an educated guess with this. Some of you, it may be a guess. I can't say that I think I would have known the answer. I'm not sure. So yeah, have a think and let's see what everyone thinks. So another 30 seconds left to vote. We've got 10 seconds left, so let's see what people think. It doesn't seem that it's updated, or nobody had any idea of what to vote. So hopefully you managed to have a vote. But I can tell you that the correct answer is measles. So here's the R0 number for everything in that table. And we see that measles has the highest R0 number by quite a lot. And that really highlights the importance of the vaccination for measles, because if someone was infected, they could go on to infect around somewhere between 12 and 18 people, who then can all go on to infect. So you can see how that could go through a whole population very quickly. If we think back to that picture of one person infecting 2, who infected 2, if we imagine that one person was infecting 18, hopefully you can visualize how big numbers we're talking very quickly. Covid-19 sits in the middle, so its R0 is somewhere between 3.8 to 8.9. Now, you might be looking at these thinking, well, I've said the R0 number, so why have I given an interval? And that's because for each illness, we don't know the R0 number. It doesn't just tell us. Covid-19 can't come along and say, my R0 number is 4. We have to estimate this using statistics and data. So by looking at the data, we estimate what we think the R0 number is. And that's why we've seen things like track and trace being kind of fundamental to collect this data to understand how the disease spreads. And we can see, say, for the common cold, the interval is small, so 2 to 3. So we think the R0 number is somewhere in that range. So that's what our data is telling us. And it's perhaps possible this number is smaller, or the range is smaller than for Covid-19, because there's a lot more data on the common cold. Because it's been around for a lot longer, we can have a much better estimate at the R0 number. Whereas something like Covid-19, it's still quite new, so we still are getting more data to get a better estimate. So it may already have improved slightly since when these figures were released. So one way that we model epidemics, and what I'll be talking about today, is using stochastic models. And I've actually seen this said a few times, which is somebody claiming that epidemiologists are just trying to sound clever by using the word stochastic, when all it actually means is to guess. So people are just trying to fool us that they're doing something intelligent when all they're doing is guessing. So is this true? Are mathematicians just guessing and pretending they're doing something clever? Obviously not. Stochastic means a process or system that is one connected with random probability. So as I've already said, I can't know exactly what's going to happen in terms of who specifically is infecting who, because there's an element of randomness. So people's behaviour can be thought of as random, so who's interacting with who. And also, if two people interact, there's a probability that the disease will get spread from one to the other, but there's also a probability it won't. So there's a random element, and that's what I mean by stochastic model, because I'm building that into my models, and I'm going to be looking at maybe not individual movements, but as a population as a whole and what their effect is. So in a way, you could think of the word guess comes into it, but it's an educated guess based on a lot of really intelligent maths going on behind it. I'm not just plucking numbers from thin air. So the common stochastic model to use is an SIR model, and this splits the population into 3 groups. So in this group, you have susceptible people. So these are people that can get the illness but haven't yet had it. Infected people, so they're infected, or recovered and removed people. So these are people that have had the illness and have recovered or are removed. So often this really translates as they've unfortunately died from the illness. Our population, we assume the total stays constant. So we can think of our population as n people, and these n people either belong to the susceptible category, infected, or recovered, removed. And so at any one time, the sum of these equals n. So if we're thinking of the time being today, well, I've not had COVID, so I would fit into the susceptible category. Hopefully no one here has COVID currently, but if you did, you would be in the infected category. And if you've had COVID but have now since recovered, then today you're in the recovered, removed category. So this is how we think of the populations forming this structure. And what we're really interested in is to see how people move between these categories and how many people are in a category at one time. So, for example, the number of infected people is really important when we're thinking of hospital capacity. We want to know the total number of infected people to make sure that we have the capacity to deal with those that might need to go to hospital. And so we can think of how people move looking at different rates. So we have beta as an infection rate, and then beta times the number of susceptibles times the number of infected represents the number of susceptible individuals that become infected per day. So it's the rate that people move from this susceptible box to the infected box. So if our infection rate is large, people become infected more quickly. Gamma is the recovery rate. So gamma times the number of infected people is the number of individuals that recover per day. So if gamma is large, people recover more quickly. So they'll move from infected to recovered more quickly. So what can we do with this model? Well, to start off with, we could look at a simulation study. So using this model, we can simulate data to try and understand how the disease may move in a real population. So even though this is simulated data, it can give us an idea of what might actually happen, as we can put all the model together and then hit play and see what happens, and that will give us a good idea. So this here is an example, just a very simple example, where we have these 2 red pies, which I guess are people, and these are infected, and our blue ones are not infected. And so when I hit play, we can see that this simulation is showing as the red one gets near people, it gets those infected, and then as time passes, infected people recover and they'll turn grey. So I'll play this. So we can see that as the red moves, more people are becoming infected, and now we're starting to see some grey out as they are recover from the illness. So this can keep going. We still have infected people, so they could still be infecting more people. So this isn't the end. But whilst we're doing this, we can see the amount of infected people, the amount of susceptible people, and the amount that are recovered in this plot here. So if I play it again, you can now have a look at this, and we'll see how the number of infected people is increasing whilst the number of susceptibles is decreasing. So here, our infected people starts to increase, susceptible people decrease as they become infected, and now recovered starts to increase as infected people recover. So that's just a simple example, and it relied on us knowing how many people were infected at time 0. So we had 2 people were infected. How many were susceptible at time 0? So that was the number of blue people at the start. And it also relied on us knowing the infection rate, so when the red infected the blues, and also the recovery rate. So that was as the red people became grey, what rate was that happening at? Of course, just like with the R number, these beta and gamma aren't just known numbers, and so we need to use a lot of clever statistical inference that's based on data to try and estimate what these numbers are. So again, it's not something I'm going to go into how we would estimate these, but this is where sort of large data analysis really comes into play. Now, with a simulation study, they can be computationally expensive, so that was just for a very small sample. Of course, if we're thinking of the UK, the population is much larger than those, I think about 50 people. And so to run this on a computer can start to become quite a lot slower, and sometimes it's not feasible to do. So what we want to do is try and solve equations to get an idea of how many people will be infected and how many will be susceptible at any one time. So instead of having to run simulations to sort of estimate it, we can actually solve equations to get numerical analytical solutions. And we do this by solving differential equations, which some of you may have come across, some of you may not yet have come across. But if you were to do a degree at Nottingham within your first year, you would be very familiar with differential equations, and you'd see just how many uses they have. So they're a really interesting area of maths. So I'm not going to go into it because you can all have that to look forward to. But that's sort of the maths that's underpinning this. And when we solve these differential equations, so we can then look at how the number of susceptibles, infected and recovered people vary with time. We find out that the R number, which actually can be written as the infection rate over the recovery rate, is really important in determining what's going to happen in the population. And it's really important based on if it's going to be greater than or less than 1. So if we look on the left, R0 value here is greater than 1. So the infection rate is greater than the recovery rate. So people are getting infected faster than they're recovering, and thus the infection will grow throughout the population. So if we look at this example of a plot, at time 0, 80% of the population is susceptible and 20% is infected, and no one is yet recovered. So if I look as time goes across, the number of susceptible people decreases to 0. So by time 30, no one is susceptible, so everyone has been infected. And we can see that the number of infected increases and then goes to 0. And by about time 40, the amount of people that are recovered is 1, which indicates the whole population. So what does this mean? It means that the whole population has had the disease at some point because they've all recovered or been removed. And this is not what we want. Because if we think, for example, with COVID, we've got vulnerable groups, and we know that COVID can be fatal, and it can also cause long-term effects. So we don't want the whole population to have got infected because we'd be putting a lot of lives at risk. We want to keep the amount of people infected low, and so we want the amount of susceptible people to be high because these people then haven't been infected. So if we now look at R0 is less than 1, so this plot on the right, the infection quickly will die out as people are healing faster than they're spreading it. So if we look again, we still start with 80% of the population is infected, it's susceptible, and 20% is infected. However, now, as time goes on, susceptibles decreases, but then stables out at about a 60%. Infections decrease to 0, and the recovered stables out at about 40%. So for this value of R, the 60% of the population don't get infected at all, and as the infections become zero, no one new can get infected. So the disease is over, because if no one's infective, no one else can become infective. And 40% have had the disease. So already this is a lot better scenario, as only 40% of people are at risk in this scenario, whereas the previous one we had 100%. Of course, as we decrease R more and more, that amount of people that have the disease decreases. And so that's really what we want to do, because we want to keep the least people getting the disease, so that less people are being put at risk. So how can we decrease this R number? Well, you'll have seen a lot of the interventions that have been going on can all be explained with looking at the model or the R number. So vaccination is really important, as this makes less people susceptible. So we saw early on that moving from susceptible to infected was beta times the number of susceptibles times the number of infected. So if this ST number of susceptibles decreases, less people will move over to become infected. And so vaccination is really important, as not only does it decrease the chance of you becoming ill, but it can help the population as a whole to reduce the amount of people that are infected that then can pass it on. So it's not sort of just a selfish thing to do to be vaccinated, it's really important for a whole population. We also have interventions like lockdown, social distancing, and all of these reduce the infection rate. So people are being infected less when we're in lockdown or when we're distancing. And we can see, because the R number equals the infection rate over the recovery rate, if the infection rate decreases, R decreases too. And that's exactly what we saw we wanted to do. If we found a cure for COVID, that would increase the recovery rate. And so if we increase that as R equals beta over gamma, if gamma got larger, then R would get smaller. So these are some of the things that could help. So hopefully that explains kind of why these interventions are important, and it's supported by the maths. They're not just sort of picked at random. So we've only looked at SIR models, but there's lots of other stochastic models that would be suitable. Well, that are used, maybe not suitable for COVID, but different ones are suitable for different illnesses. So one example is an SIS model. So here the group is just susceptible and infected. So once you've become infected, when you recover, you become susceptible again. So an example of when this might happen is, for example, the common cold. You can keep getting it once you've recovered, so you never become sort of immune to it. An SEIR model. So this has an extra one called with exposed. So at this point you've been exposed to the illness, so you have the illness, but you might not be infective yet or showing any symptoms of the illness. An SIRD model is an extension of an SIR model, and it splits the last step between deceased and recovered. And so this allows a bit more flexibility when moving from infected to recovered or deceased, because previously we were assuming the same rate from dying or recovering, whereas in actual fact it's probably different rates. So throughout, I've been having to make some assumptions for the mathematical model and when we were using these differential equations. And these are some of the assumptions I've had to use. So everyone is as likely to get infected. The rate of recovery is the same on average for everyone. An infected person is as likely to pass a disease to anyone in the population, and no one leaves or enters a population. So the final question is, do these model assumptions seem valid to you? So again, you should be able to vote on whether you think these ones seem valid. So about 30 seconds left to vote. So yeah, have a think about some of these assumptions. Do they seem valid? Do all of them seem valid? Are there some that don't? And because as mathematicians, this is often what we have to do, is think about the assumptions we're making and thinking, are they good assumptions? Are they bad assumptions? So 10 seconds left to vote. And so we've got a bit of a mix, but over 70% of people have said no. So I would agree that I think the answer would be no. These assumptions don't seem valid to me. That perhaps it's not always completely cut and dry whether they are. So you might be thinking, why have I told you this model if the assumptions aren't valid? And so just to go through a few quickly of why I don't think they're valid. We've seen, for example, rate of recovery could vary with age, so it's not the same for everyone. An infected person is as likely to pass a disease to anyone. So I'm much more likely to pass the disease to my family and friends that I'm seeing, as opposed to a random person in Manchester where I'm not going, whereas this model doesn't account for that. So yeah, why have we done this then if the assumptions don't seem valid? So first of all, like I said, that we're looking at large populations and assuming a lot of averages. So sometimes in maths and statistics, even if an assumption is violated, the models can still be useful, and sometimes the effect of that violated assumption isn't as large as we might think. So we can still gain insight, and as long as we understand sort of the assumptions and how, if they break, the effect that might have, we can still get information. So we can't just say the assumption's not valid, so we'll do nothing, because we often need to simplify the problem. The other thing is that the model I've shown you is really just a taster of what maths and statistics can do. So this SIR model is a building block, but it can be built on a lot to add in a lot more of these assumptions. And that's where a lot of the new research is coming in, is to try and expand these models to fit with new topics. So we can create much more sophisticated models that might be based on the SIR model, but they might take into account subpopulations, so household, work groups. They can also take into account different risk groups. So we had that infection rate and the recovery rate, but we could change that so it varies for different ages or different characteristics of a person. So yeah, I really want to highlight that whilst I've shown you a simple model that is still very useful, a lot of the research and when we're actually using it, we're adding to these models and making them more complex, which is a really exciting area of maths, especially when it is such a useful and real application. So for this talk, I want to leave on this quote, which is, "Nothing in science has any value to society if it's not communicated, and scientists are beginning to learn their social obligations." So right at the start, we looked at those newspaper headlines, and we saw there's confusion around maths and statistics. And so doing a degree in maths, you'll get to learn loads of really interesting maths. So we've seen differential equations, these stochastic models, the large data sets I've talked about. They're just some of the areas and some that particularly excite me. But you also will get a chance to communicate maths, because for what we do to be sort of really useful for society, we need to be able to communicate this so everyone can understand it, and also for it to be implemented. So if you want to learn more and you've enjoyed this talk, there's a taster lecture on probability by my colleague Peter Neal next Tuesday at 11, and I believe that there's a link in the chat for that. I'm also the co-creator and editor of the Women in Pride in Maths newsletter, and again, I believe the sign up is in the chat for that. So if you're interested in hearing about news, funding opportunities, and just celebrating women in pride in maths, that's the newsletter for you. So thank you for listening.